Hello and good morning, everyone. Welcome on this webinar. Thank you for joining us today. My name is Florie. I'm the Communication Manager at SERMA Group. So we will wait 1 or 2 minutes before we begin to give everyone time to join. And in the meantime, let me briefly introduce today's speakers. First, I would like to welcome Gilles Leborgne. He's a member of the Supervisory Board of SERMA Group and former Executive VP of the engineering at Renault and PSA Groups. Next, Tenzing, our Energy Business Manager, will give you a brief introduction of SERMA Group and our energy capabilities. And finally, Cyril and Thomas, our battery experts, will lead the technical session. I would like to mention a few practical points. So this webinar is being recorded and the replay will be available afterwards. And you can ask your question in the chat. We will answer as many as we can at the end of this webinar. So I can see more participants are joining us, so we can begin. Thank you once again for being here today. Gilles, it's over to you.
Okay, thank you, Florie. I hope that you are hearing me well. So good morning, everyone. On behalf of SERMA, I am absolutely delighted to welcome you at this webinar. Looking at the registration list today, we just did that before the opening the session. We have around 150 professionals joining us from across the entire ecosystem, colleagues from major OEMs, tier 1 suppliers, specialized laboratories, and engineering partners. So thanks you for taking the time to join this critical discussion. We are gathering at a critical moment in automotive history. By the way, the transition to battery electric vehicle is no longer a future projection or a regulatory compliance exercise. It's an industrial reality as we speak. And this reality is gaining massive momentum in the market worldwide. By the way, between Jan and May this year, we saw a spectacular growth of BEV sales in Europe, up more than 35% year on year, pushing the electric market share at 20% plus. Of course, this acceleration has been heavily reinforced by the conflict in Iran and its impact on oil costs. Nevertheless, BEV increase will not stop because that's the best solution to global warming effect. But as we scale up, the nature of the challenge is shifting. We are moving from early adopters to mass market, and the mass market demands an uncompromising balance of performance, reliability, and low cost. So to sustain this momentum, our industry must solve the primary friction points for the everyday consumer. Range anxiety is rapidly giving way to charging anxiety. The end user doesn't just want to travel far, they want the refueling experience of a BEV to be like an internal combustion engine. Consequently, fast charging has become the ultimate competitive battleground for OEMs. This customer expectation is driving a profound architectural transformation across our vehicle platforms. And you know well the generalization of 800 volt or even above technologies. Shifting from 400 volt to 800 volt topologies is a massive leap forward. Doubling the voltage allows us to cut the current in half for the same power delivery. This means, on the positive side, radical reductions in charging times, thinner, lighter wiring harnesses, improved thermal efficiency across the entire powertrain, from the power electronics to the electric motors. But, and you know that very well, there is no free lunch in physics. Higher voltages, higher current density during ultra-fast charging, and tighter packaging put thermal and electrical stress on the battery cells, modules, if any, and packs. More than ever, a systematic approach is needed in the design. So this brings us to what I call the OEM trilemma, because the core challenge facing every OEMs and tier one supplier today is a complex trilemma that required balancing three distinct and often competing pressures. First, high performance, of course, customer demand excellent autonomy, high energy density, and fast charging capabilities under all temperature conditions. Second, affordability. To achieve true mass market adoption, we must aggressively reduce costs. This is driving a massive diversification in cell chemistries, forcing us to master everything from high energy NMC to cost-effective LFP or LMFP. And looking ahead, of course, to sodium-ion and solid-state alternatives. And third, absolute safety. This is a non-negotiable foundation. We see a radical shift from the old, I would say, 5-minute rule before thermal runaway to the no thermal propagation at all rule. Indeed, a single thermal runaway event can compromise a vehicle line, tarnish a brand's reputation, and more importantly, shake public confidence in the entire e-mobility transition. Consequently, the no thermal propagation principle is now the rule for energy densities higher, optimize thermal management system to the absolute limit, and cut structural weight out of the pack casing to reduce cost, the margin for error shrinks to zero. This is precisely why we are here today and why SERMA has invested so heavily in state-of-the-art misuse and abuse testing facilities in order to be your partner in battery safety design. To guarantee safety, we have to simulate the worst-case scenarios. We must push this high-energy, high-voltage system beyond their design limits to see exactly how they behave when things go wrong. SERMA's specialized facility that we will see after are engineered to safely execute the full spectrum of destructive and abuse testing, electrical misuse, thermal abuse, mechanical and environmental abuse. By cooperating advanced testing platforms and leveraging deep expertise in gas analysis and physical chemical failure mechanism, SERMA provides the automotive industry with all the skills and facilities needed to bring this complex 800-volt system to market with absolute confidence. So over the next hour, our expert will take you inside this advanced design and testing protocol. So thank you again for your presence today. I wish you all a productive, highly collaborative webinar. And now I hand over to Tenzing. Thank you.
Thank you very much, Gilles Le Borgne, for this excellent overview of the strategic challenges that the industry is facing. Good morning, everyone. I hope you can hear me correctly, hear me well. My name is Tenzing, and I'm glad to take the microphone for this webinar today. I am sales manager for SERMA on our battery department. So really happy to be here with you today. I will now focus on how SERMA translates these into concrete solutions for the industry and for our customers. Let me tell you a little bit more about SERMA before handing over to Cyril and to Thomas, who will talk deeply about battery abuse and safety validation. So first of all, a few figures about SERMA Group, about the company. So 35 years old company, 1,500 employees, and more than 30 sites around the world, mainly focused in Europe, Tunisia, and the US. You will see we are very diversified in terms of customers we address and in terms of fields where we are working for. And more specifically, of course, the automotive industry is leading a lot of our activities, but not only. As you can see, aviation, space, defense are going also very strong, and stationary applications, sorry, also very strong into those topics. So this is the figures from the company. And here you can see on that slide a little bit more details on specifically the department we have within SERMA. So first, this energy department that we created about 15 years ago now, where we address everything related to e-powertrain, batteries, and stationary application when it comes to batteries itself as well, as long as hydrogen. We will detail this a little bit after. And what is very important to see and to know is that SERMA historically started from the electronic and from the component itself, from failure analysis. So we have also deep understanding of the electronic globally, from the component to the system, as well as microelectronics. So here we have laboratories doing material study analysis as well. Um, Design and manufacturing for microelectronic too. And because we see potential failures everywhere when it comes to electronics, so we are very specialized into that. We also open the cybersecurity and safety department, covering embedded system infrastructures and so on, to support our customer to make better product, more reliable products, and safer products as well. If you can go on the next slide. Okay, thank you. And these are our locations. So historically, we were a French company, so we grow from France with more than 20 sites in France, now in Germany, Spain, Tunisia, and the US. We will detail a little bit more where we have today our sites for battery safety validation and validation more globally. But before that, I would like to show you the product we are working on. I would say mainly within this energy and e-mobility or battery division. So we are a testing and engineering platform. So you will see we've got a large panel of capability, sorry, for testing, and of course design team and engineering team to support beyond that testing part. So we address today power electronics, so that will be converters, DC-DC, converters, sorry, onboard chargers, inverters, batteries, so from cells, modules to complete pack level, including full system and vehicle as well, hydrogen and e-motor or electric drive units completely. So a quick overview, focusing on where we do testing for energy and e-mobility globally. So you will see we have 8 testing sites and more than 25,000 square meters of testing platforms between France and Spain. So historically, we started with one facility with a group of people, and this group of people grow. The needs in the market that we follow also grow rapidly in the last few years. So we expanded our capacities to join the need of the markets, be closer to our customers as well. And that's the reason why now we have different sites, different team dedicated to the testing requested by our customers, again, from cell to complete pack system, from abuse test to electrical test, mechanical test, durability test, and so on. So quite diversified capacity and type of tests we can address today from those sites. So one of our key, I would say, strategy and the way we see we can approach and the industry today is covering as much test as possible, coming from the electrical test, environmental test, mechanical test, abuse, and homologation. This is the case for all the products we are working on. And I would say outside of the capabilities which are strong within SERMA, we have also a strong team going on with the R&D, understanding the product itself, and that's the reason why outside of of the capacity we can cover, and we can support the industry on the next challenges and the challenges we are facing today within the R&D up to the homologation of those products. So we'll now hand over the presentation to a deeper understanding and concrete talk to Cyril and to Thomas regarding safety and validation for batteries. Thank you very much.
Thank you very much. Thanks, Tenzing. Hello, everyone. So today, in fact, in this technical part of the webinar, so we'll try, in fact, to show you a bit the challenge of battery safety validation. So first of all, it will be more something like theoretical aspect with where we'll speak about technologies and risks and failure mechanism. Then after we'll discuss about the effective validation strategy. So this is more related to standard, but sometimes, as Tenzing mentioned, you need to go beyond the standard, and then for this you need to adapt your abuse test part, let's say, in order to try to characterize better as possible. So this will be the first part. And the fourth part will investigate failure. So after test, what happened and how we deal with this kind of, let's say, procedures. So let's start. First, well, you know, what can happen sometimes is that there is a failure. So basically, lithium-ion battery, when we do a risk analysis of lithium-ion battery, what you see is that, first of all, when thermal runaway starts, you see that this flame that you see, this is basically electrolyte, which is a flammable liquid that took first fire, let's say. And then after you have, of course, dangerous gas that evolved. So basically, they are emitted with the before when it's venting, and then after, of course, there is combustion gas also that came. You have also different chemistries, LFP, NMC, LCO, for example, that have different thermal behavior. So this is also something that, as a risk analysis, you have to take into account. And for, of course, something which is very important is that it's sensitive to temperature. So for safety, of course, from 80 degrees, you can start to be, let's say, a bit afraid in terms of safety. Of course, electrolyte is sensitive below, but at least for safety, it starts at 80 degrees, around at least. Of course, SERMA, we are very, very into it. So it means that we test a lot of packs, and we follow, let's say, the technological innovation that are put that are placed in the different systems in order to avoid and to limit this propagation. So this is something that we are very common at SERMA. From theory now, you see that at least from kinetic point of view, a thermal runaway, you will heard a lot of stories about, let's say, fire brigades that try to put a pack into water, and after 2 weeks, they put it up and it starts again. Let's say the thermal runaway start again. So in fact, here it's everything is kinetic. So it means that when you start to have an issue, so an internal short circuit into your cell, for example, there is a different moments where you can stop, let's say, or at least limit the thermal runaway to happen. So it means that you produce enough, or at least you put enough cold in the system to limit the heat to dissipate and to propagate. But at some point, you reach a limit, and this is this red part here, and this limit means that you cannot go back. So it means that even if you put a lot of cold in it, the thermal runaway will happen, whatever you will put as a cold inside. So this is very, very important to understand this, because it means that you will see after in the next slide that there is a propagation of the heat in the cell. And this propagation, at some point, of course, it's because you create some heat, and you will see that in the next slide. So what I go on it, that you have in fact more and more small mechanisms. So you start by a failure mechanism inside the cells that initiate the internal short circuit. And then after this will create a first heat, and this heat will decompose the passivation layers, this SEI layer on the anode, that will also create a heat itself. And this heat will go to decomposition of electrolyte that will also create a heat. So you see my point is that more and more you will increase the temperature of your system without putting more temperature in your system itself. So it means that this is a step-by-step, let's say, a configuration. This is why you can stop at some point let's say the reaction by putting cold, inside it. But of course, sometimes you cannot avoid the last part, which is the reaction that go to thermal runaway. And this is depending on the cathodes that you have in your system. Either you go to 400 to 600 degrees, either you go even beyond this at more than 1000 degrees, depending on if your cathode itself is able to produce oxygen in your system. This is the case, for example, of NMC cathode versus LFP, where LFP will not produce oxygen. So this shows you that the reaction and also the components that are inside the cell are really critical, and let's say that the reaction at the end depends strongly of these parameters. Now, well, on the market, this also comes next, will be, let's say, sodium-ion battery. And this year you will heard a lot of things as well, because people try to promote it, of course. But when we think about it, sodium-ion battery, when we speak about the risk analysis, you have still a flammable liquid electrolyte, it's still carbonates. So basically here you have still the problem of having something which is flammable inside your system. From sensitivity to temperature for safety, it's also the same. You are around 80 degrees. You are also having dangerous gas due to electrolyte again. And also what's something which is very important in your risk analysis for sodium-ion battery is that you have a very large possibilities of electrode materials with different thermal behavior. We have seen that for lithium-ion batteries, you have NMC, LFP, which are most well-known, let's say. But for sodium-ion, you have much more possibilities, which means that, of course, every material itself have a different thermal behavior and can behave differently. So this is why here it's very important to test as well for sodium-ion battery. And at least at SERMA, we already test quite some, and we don't have all the time the same results depending on the chemistries. The same also happened for the next generation. So it means that here the lithium metal battery first. Here there is some fire. When it takes fire, you see that the fire is not exactly the same. Here it's not the electrolytes that burn. It's mostly, and you see some particle in this video, in this picture here, and these particles are lithium metal that is melted. The disadvantage also the risk analysis is that this battery is working from 80 degrees and that the lithium metal is melting at 180 degrees. So it means that here to control it, it's not good, because also when you want to cool down this kind of system, you cannot use water, because water can react with lithium metal, and you will produce some hydrogen that could create a very huge reaction in comparison on what you see at this picture here. So also at SERMA, we have already tested this kind of technology, so we can also see, let's say, and try to understand the mechanism, and we have seen that interface reaction are very important. For the next one is solid state, and again here it's very important to test, because first of all in solid state you have different possibilities. You have with or without lithium metal that we discussed just before, and also with or without a bit of liquid. Currently in the market you will see people that claim to have a solid state battery, but in fact they have liquid inside a bit, so they call it hybrid system. So this change a lot of things in terms of thermal runaway and in terms of reaction. and which means that it's more and more difficult to track it in the system because the solid has not the same thermal, let's say, ability to propagate the heat than the liquid. And this will, of course, be more difficult to track. And also, again, at SERMA, we already have tested such technologies, and we also try to adapt our, let's say, way to measure for this kind of battery. So now I speak about technology. I go for, let's say, standards. And from standards point of view, there is an evolution, and Gilles also talked to it, is this evolution about this R100. So this R100 is dealing with EV batteries. And from Europe, now on, it's, let's say, you have to have no fire or something like this, 5 minutes before to have any fire. So to allow you to extract from the vehicle before there is a problem. And in the evolution of the standards, now you have to prove it. So it means that it's not anymore something that with a theoretical aspect you have to prove it. Now you have to prove it with tests. Know that at least there is also this evolution in China, but in China now they are able to, let's say, in the standards that there is it should not catch fire or explode after thermal runaway. So this is also something that you need to take into account when you do a risk analysis of this kind of batteries. About the standard itself, you will see that there is a lot of standards that also at SERMA we can cover. There is no problem. Here it's just to show you that depending on the application that you will have, it's very important to select the right one, of course. So you have the EIC 62619 for industrial battery, but after if you go more for transportation, it's UN 33.3. Or if you are also in BESS system, it's the UL 9540. So you see that there is quite difference depending on the application. As you can, let's say, guess, it's not exactly the same test inside. So it means that when we speak about validation toolbox, so it means
Excuse
the kind
me,
of test.
Cyril. Excuse me, just for me. Someone is speaking in French. I don't know. I don't know where is it. You hear it? Okay.
Can I continue or?
Yes, someone is speaking with you.
No, no at all.
Okay, thank you. It's okay. Thank you. Sorry, Cyril. Thank you.
No problem. So at least here in the validation toolbox, we have different types of abuse tests from standards. So mechanical test, electrical test, thermal test. And for each test like this, so there is, let's say, penetration, for example, crash, immersion in salt water, etc., etc. So the goal is not to make a list or a catalog here, it's just to show you that it exists. But on the other side, what you see after for external short circuit protection, for example, you have different standards, and each standard place limits. So in fact, for example, for external short circuit, you will have different value of short circuit that you have to maintain. So this parameter can be tuned depending on the standard. And of course, some are more problematic for cell, or at least it's more constrained for your system, and some other not, of course. In the validation toolbox as well, so we are equipped at SERMA. So we are equipped because it's, let's say, it's a basis for standard validation. We combine electrical tests, environmental tests, and abuse tests. So it means that, well, this nice picture of explosion doesn't happen every time, of course, when you do the standard. So the goal is to combine all results from electrical, environmental, and abused in order to validate any standard. And it's something that is very important to understand, is that this is a combination of three that after allow you to, let's say, to go on in the market, let's say. However, when you come for a certification, I would say, according to R100 03 or R100 05, for example, It means that on our side, we will ask you, are you sure that the product can sustain the test? If you are sure about this, of course, then we can support you with the certification. And let's say by a partner of SERMA, UTAC, Ali, or so on. And most of the tests can be performed at SERMA facilities, so this is not an issue. However, well, sometimes you can say, I'm not sure for one of my tests, etc., etc. So I need a pre-validation to ensure that it passed the test. So this safety test, therefore, can be performed before to go for certification to ensure success, because of course it costs a lot of money in order to go for certification. After, of course, you can also say, I'm not sure at all that it can pass the test. And in this case, at SERMA, we are able to do a construction or risk analysis of your system. And once the design is validated by our teams, the test can be performed as a pre-validation before to go for certification. So this is here, let's say, our validation methodology. In order to be sure that at least we sell you something that is suitable for you. About the battery behavior from cell to system, sometimes you really don't know of your system. So it means that, as I mentioned, the battery is a very complex system we have seen. So here in the picture that you see, we go for pack. For example, you have a pack to develop, but the pack itself is composed of modules. The module itself are composed of cells. And inside, there is as well electronic boards, BMS, battery management system. You have also more and more new technologies like cell-to-pack system or cell-to-chassis. So this is something that also you need to take into account, which means that it can even be more complex system. And also that we don't think or at least we start to think about it because we start to also see it, is the accessibility of the BMS data using Wi-Fi or Bluetooth, which can at some point be problematic for safety, cyber security, and so on. So also at SERMA, we can support on this aspect. So for characterizing better your battery in order to, let's say, build it something very robust from a safety point of view, we have this test plan toolbox. So it means that we'll test as well the performance, the environmental part, that your battery, for example, at some temperature is okay, and also the safety part. So there was two contexts that you can come for this. You come with already a product, and this is the case that I discussed just before. So we do a construction analysis, a risk of construction analysis. We identify the weaknesses from this aspect that we need to improve. We improve it with you after modification. We set a list of tests in order to confirm that the improvement, including the test protocol, let's say, are validated. We perform the test and we support you with the validation. The other contest is more like you request design or support for design a new product. And this is also something that we provide. And in this way, we will have something else as a methodology, as an approach. So we'll do a cell benchmark first to select the most adapted cell to the targeted use. We will also try, and this is very important, to understand the cell limitation to fix the safety limit. So here we will explode, let's say, the cell in order to understand very carefully the safety limit. After, we will prevent the thermal propagation at module and pack level. So we were at cell level first and then at pack or module level. And after, we go to system designs with choice of material, thermal simulation, lifetime prediction, etc., etc. And we finally go to product validation. So I will take over now the, let's say, the lead to Thomas, to speak about this.
Thank you, Cyril, and hello, everyone. So like Cyril said, when one of the customers, for example, needs to define a product and select a particular cell or module, there are standards and certification to validate to be able to sell transport or to use the batteries in different cases. So you have to, for example, respect the UN 38.3 or the R100 for road transportation or the UL 9540 for BSS. However, it is important to be able to better understand the product limits and the behavior under the stress. So this is why, you can go to the next slide. This is why, for example, understanding the limits and behavior of the cell allows to implement, for example, the right cooling, the right thermal barriers and safety measures to prevent electric shock, mechanical damage, or to just mitigate a thermal propagation throughout a whole product. So these kind of tests are realized at every level of the battery pack, from the cell to the module to the battery pack. For example, a TPT test or a thermal stability test allows to better see what volume and what type of gases are ejected out of a specific cell, as well as their gas temperature. And this is crucial to calculate and determine, for example, the right venting of the cell itself, but also the ones at module and pack level. So this device that you can see here allows us, for example, to check very thoroughly the whole behavior of a cell under stress, and here specifically in an enclosed area. And we can have very precise views and sensors return on what's happening at cell level. Here I can show you a high frequency video of a cell venting going off. This is something that can really help the design of a cell, or at the module level, to be able to properly see the flow of the gases coming out of the cell, or the venting itself, in the design of the venting itself, and to check if it's properly venting the cell, or if there is an uncontrolled venting, as we call it. It's when the fire goes from the venting of the cell towards the sides, and there is a rupture in the casing of the cell. So this is something really interesting especially for cell manufacturers and module manufacturers. Something that we can do, especially in this device, but for a wide range of tests that we perform, is to check for different use in different cases, different results in different configuration. So here we check, for example, the behavior under different SOC levels of a cell. So we have the pressure increase depending on the state of charge of each cell. So going from 100% from 30% to 100%. And with this information, the manufacturers can better understand what's happening in the battery, and then take the countermeasures to mitigate the results and the impact on the environment. Of course, here we have a nice IR view of a cell reaching thermal runaway. That's something that's really useful at every level of the test that we perform. So from cell to module and pack level. It really allows us to better understand what happens inside of the item, and very useful for the customer. So we have here a slide to illustrate what happens when there is a thermal runaway happening here at this poor guy, let's say. So here one of the cell reaches thermal runaway, and as we will see, it will propagate to the other cells. Here there is a full propagation from one cell to another and to the whole module. So at the beginning, it's usually one cell reaching thermal runaway from the next one, from the next cell. But then when there is a high temperature and a very hot environment, multiple cells can reach TR at the same time, making for a big pressure and a fire surge, as we can see. tests. So here is a test that we could perform, for example, just to illustrate what we can do and what the sensors we can use. At the start of the test, we have just a regular pack or a dummy pack, I would say, with cells, active cells inside. We will use temperature sensors at precise points on the back, both from the customer needs and from the input that we can advise to the customer. So we can check for the gases temperatures, the cell temperatures. It gives us insights on what cell reaches TR at what moment and in what part of the pack. We have multiple cameras and IR cameras that allows us to better understand what happens outside of the pack, and also, of course, a wide range of sensors that we can use. After this kind of tests, we usually perform a post-mortem analysis, which gives us a lot of information on what happened. So as I previously showed, the small bike catching fire, here it's a bit different. We have only 2 cells that reached thermal runaway. So opening the pack and performing the post-mortem analysis gives us a lot of information on what happened. And we can open the pack, remove the cells, check for the spacers states. We will do electrical checks, mechanical checks, everything that's really interesting for the customer and from the customer's demands, and but also from our own experience. Yes, and so like I said before, those tests can be performed at every level, and we have the ability here at SERMA to perform them at every level. From the cell, we can perform thermal runaways. Thermal runaways are the main test that we perform at every level, and it gives us really a lot of information on the safety of the batteries and how they behave and how they can impact the product and especially the customers and the users. So we can trigger a thermal runaway by night penetrating or pad heating, or also overcharge. Although overcharge is a bit different because you add a lot more energy in the cell than that's what I mean, a lot more energy than necessary. For this kind of test, we can run a gas analysis, which gives us a lot of information also on what happens when the gases are ejected from the cell. We also run electrical tests to see the behavior and the safety protection on the cell from ESC, external short circuits, to different tests. At module level, we also perform thermal propagation, the same as cell level, but a lot more of external short circuits and also resistive external short circuits that are very interesting to check the efficiency of the eventual fuse or weakness on the bus bar in the module. Yes, and yeah, it's going to be the same for pack level, although external short circuits are going to be more focused on the fuse device that's inside of the pack and check for validation regarding the certification, for example, the R100. So like Cyril said, we will check for the pre-validation of the test and check that the fuse works properly before going to the R100 certification. And at system level, we can now perform full vehicle thermal propagation, but also immersion tests and external fire tests, for example, in our new facility in Neuville-aux-Bois. So that's something we're very proud of and very interesting kind of tests. I will hand over back to Cyril now. Thank you.
Yeah, thanks, Thomas. So as you have seen, so there is a lot of, let's say, possibility from let's say, testing abuse test on batteries. But also, I mean, there is this last small part about failure analysis, because as you will see, we also use abuse tests for failure analysis. So at SERMA, we have also this division. So basically here, a failure occur, and you have seen here that it's happening in the container, like for storage, energy storage system, BESS. And here we try to understand why there was this failure. Sometimes everything is burnt, so you have nothing left than this, and your only solution is basically to try to reproduce a defect, because, well, when everything is burned, sometimes it's not easy to find a clue of what happened. So basically here, you need to investigate this and to make hypotheses out of it. So you analyze first electronic part, like BMS part, BMS analysis, and you try to understand if there was issue on this aspect. Here, our conclusion was no, for your information. And after we check battery, there is systems that are still alive. So here, where we were having some lithium plating part, which, let's say, is the precursor at some point for dendrite. So it's not recommended in batteries, in cells. And as I said, sometimes, I mean, failure analysis, I mean, we need to reproduce. So in fact, when we define hypothesis, we test our hypothesis like temperature or something like this, and we try to reproduce the defect. And this is why we also need abusive tests for this part too. As a conclusion, so we discussed about the challenge of safety validation. And let's say that from challenges, we have seen that there is a diversity of technology. There is different failure mechanisms, which are due to the technology itself, and also different battery behavior. If it's an NMC, if it's LFP, if it's a sodium, if it's lithium metal, etc. And finally, the limitation of thermal propagation, which is also a huge challenge for the battery industry, at least automotive one. And also for the others, BSS and so on, is also very important. So basically, at SERMA, we try, in fact, to, let's say, support you in the full range of this product lifetime. So in fact, that when you design the first version of your product, we try, let's say, to support you in the development with our experience, our own experience, expertise. And we can also perform the first test according to targeted standard or slightly beyond. So basically, this is what Thomas show you in both parts, and the design first, when we try to reach the limit, and the second part when you try to, let's say, go a bit beyond or at least around the standard in order to go for validation, let's say. And the third part is pre-certification and certification tests, which are homologation, which are very, very important after to go on the market. Finally, when there is an issue, if an issue occur, you go for failure analysis with reproduction tests, which means that, let's say, abusive tests are very important in the full, let's say, lifetime of the product, and we can, again, support on this aspect. So thanks for your time. Thanks for listening to us. Now we will open the, let's say, the discussion. If there is some questions, so if we have no time to answer to all your questions, already know that we will contact you a bit after the, let's say, the talk, and we will answer to all of it. So let's start the first question, maybe. Do you have experience with 21700 HP cells? From at least from safety point of view, yes, there is no problem. It's a test that we can perform. That we already performed as well. So all on this aspect, there is again no problem at all. Is there?
Yeah, at cell level, we're not really limited by the type of cell that we can experiment on.
So do you? Okay, Tenzing already, let's say, answer to one question. I've tested the latest 788 ampere hour LFP cell used for next utility scale project. At least I'm not sure that this one we tested. Tell me if I'm wrong. Otherwise, I mean, we already test cells which are a bit below this part. There is no problem at all. As we mentioned, in fact, we already test even vehicle at vehicle level. So just to let you know that for us is not an issue, at least to test this kind of cells.
Yeah, we have tested a wide range of cells from very low amp hours to very high. I've personally never tested 788 amp hour LFP cells, but I don't see any issue with this. We would just test the cells in our module facility, let's say, module test areas, since it would be a bit more energetical.
And as Tenzing mentioned at the beginning, in fact, our facility is designed with cell part, modules, and pack of system itself. So depending, of course, of the energies, there is no problem to perform this kind of test.
Okay, so Mansuk is asking, is thermal pad trigger installed inside of cell or external surface? So here at SERMA, we have and we make custom thermal pads for our customers. However, we install them at on the external surface of the cell since we don't manufacture them. However, some of the cell manufacturers can install an inside thermal pad. We have tested this for customers. It works pretty well. However, the manufacturer of the cell has to do it.
So after I can answer as well. Do you perform live test for calendar application and provide lifetime estimation based on the application temperature profile? Yes, of course. So basically, in fact, our strategy here is that we have modeling teams at SERMA Group, and there is no problem at all to both perform, of course, tests and after to design models behind this to combine both of them, of course, in order to propose you a best estimation of lifetime.
So Arjen, can you elaborate about the requirement of UL 2271? Yeah, this is quite of a long answer, so I would advise you to send us an email and we can get in touch with you and answer you more thoroughly for this question. How many samples are typically needed to validate a battery behavior during a thermal runaway event? It really depends on your design and what you are expecting and what you want the outcome to be. It really depends.
And if we're on laser thermal runaway to again introduced you want to answer to this question?
We started looking at it and we are working on a solution for this.
What else? To validate a design, how many identical stress tests are conducted? Is there good repeatability in the stress tests? You want to?
Again, it really depends on the customer and how confident they are with their design. But usually, of course, a few. It will be different if it's external short circuit tests or thermal TPT tests. So yeah, it really depends, but usually it's quite a few. It really depends on the maturity of the product.
So what else? So after, so there is a lot of question about the standards that we can perform, the equipment that we have. So we can contact you. There is no problem at all about this question, since they are not necessarily technical, I would say, but it's not a problem at all to perform this kind of test for you. We can discuss depending on the size, etc., of the cells, etc. So there is a lot of parameters. This is why here I think it's not the right moment to tell you this kind of things. But of course, we can discuss and send you an email about this to discuss directly with you in order to have more info.
Are you able to perform tests associated with explosion risks due to accumulation of tear gases inside an enclosure? I would say yes. I would need, of course, more information about the test itself, but yes, we can.
Yeah, at least here, what you can see is that all the time when you have a request like this, we need a bit more information. So of course, if it's standard, directly standard, for us, we can answer yes, no, or depending at least on the size as well of the system. But at least when it's something a bit critical, let's say, or something which is not going from standards, we need to discuss directly with you, and the team are directly taking contact with you in order to, let's say, try to have more info on exactly what you want, and also discuss with their own expertise, in order to, let's say, provide you the best solution compared to your needs. So I don't know if there is other questions. Someone is typing. So let's just wait a bit, and after, I guess we can take this last question and hand over the webinar if it's okay with you. So at least once again, I think we can. Is it okay? I think. So for, let's say that we can answer after to all, let's say, different things. Again, we'll keep you in contact with the right people at SERMA in order to provide you answers about the questions that you have here about the different standards and so on. So don't hesitate to again contact, and we will get in touch with all of you. So thanks again for your time. You will find again this webinar soon, I think, Florie, you want to hand over?
Yes, you will receive an email shortly with the replay. And if you have any additional questions, don't hesitate to send them back to us by email. Tenzing will be your main contact. And of course, if you would like to visit our facility, we also be very pleased to welcome you on our sites to show you our infrastructures. So thank you to all the speakers, and thank you all for your participation today. Thank you, everyone. Have a great day.